Hey everybody, I want to take up one of the questions from yesterday's note for 2.3a, and then I'm going to move on with our note for 2.3b. Now, I've picked one of the questions from our textbook, which is from page 276, and I'm thinking question 26 on page 276 is slightly different than the others, so might be a good place to start. So it says, what is the initial temperature of 1.5 kilogram piece of copper that gains some energy and it reaches a final temperature of 150 degrees C? What is T1? Okay, so we're told a number of things. We're told the mass, 1.50 kilograms. We're told that it is copper, and the C value for copper, I believe, is 390 or 3.9 times 10 to the power of 2 joules per kilogram degree C. We're told the final temperature is going to be 150 degrees C, and that the energy that was added, the quantity of heat, is 2.47 times 10 to the 4 joules. Okay, and our unknown. Okay, so there's our given, and there's our required. So my approach now, I'm going to use the one formula we have, Q equals mc delta T. And I'm going to put my numbers in. I could rearrange the equation to solve for delta T, but I'm going to actually just go ahead and put the numbers in. So the Q value, it tells me initial temperature, it was heated to a final temperature. So I know the Q is positive. Right? Again, sometimes that's not made very clear in the question. So Q is plus 2.47 times 10 to the 4. Mass was 1.50 kilograms. The C is 3.9 times 10 to the power of 2. T2 is 150 degrees minus T1. Okay, so I'm going to take my 1.5 times 3.9 times 10 to the 2 and drop it down here and divide it into my 2.47 times 10 to the 4. Right, so if I do that, got my calculator here, 2.47 divided by I'm getting 42.2 equals 150 minus T1. So I'm going to take my T1 from here across the other side as plus T1, and I'm going to take my 42 across as minus 42. So T1 equals 150 degrees minus 42.2, and I'm getting 107.8 degrees C was my starting temperature. Right? Now, again, just as a quick check, I'm noticing that my temperature is lower than the final temperature, which is right. If I've heated it, my starting temperature couldn't turn out to be 200 degrees, and it finally ended up at 150. Right? So again, always kind of watching to make sure that everything makes sense in terms of positives and negatives. Okay, so Q equals mc delta T. Nice and straightforward. Mass in kilograms, temperatures in degrees C, and the C value right off the chart. So again, look at what type of matter it is. Sometimes even looking exactly what our sorry, I got distracted here. Looking at the quantities of heat. Okay, so I want to move today to 2.3b. Okay, 2.3b is really just a short little note here, which is an extension. So here it is here. So this would be 2.3b. and it's called the principle of thermal energy transfer, or the law of conservation of thermal energy. In Energy 1, we talked about the law of conservation of mechanical energy, right, where mechanical energy is conserved, mechanical being kinetic plus gravitational. In this chapter, we're going to look at the principle of a law of conservation of thermal energy that says when thermal energy is released, it's got to go somewhere else. Right? So what that means for us, and the long and the short, is right here. If I take a warm object and I touch it to a cooler object, the warm object is going to lose energy. Right? So it's going to cool down. The cooler object is going to gain energy. It's going to increase in temperature. And the warm object will continue losing temperature as the cool object continues gaining temperature until ultimately they reach the same final temperature. Right? So they will continue to transfer heat, from the warmer to the cooler until the temperature of the two are the same, and then there will be no more thermal energy transfer. So that's the whole idea here. So I'm going to have two objects now. One has a Q equals mc delta T, which is talking about energy being lost. And one has a Q equals mc delta T, which is equal to an energy being gained by the cooler object. Okay, so thermal energy now being lost by the warmer object, okay, until it gets to T2. It will stop when it gets to some final temperature. That final temperature is the same T2 that the cold one will reach, and when they're the same temperature, energy will stop transferring. So the cooler object is going to gain thermal energy. Okay, and because energy can't be created or destroyed, I know that the Q lost by the warm object is going to be equal to the Q gained by the colder object. Right? But one is negative, right? The Q lost is going to be a negative number. Q gained will be a positive number. So I can't say Q lost equals Q gained mathematically unless I put a negative sign in there. And the reason why the negative sign has to be there is because mathematically the total energy change in the system has to be zero. Right? The energy change in the system has to be zero, right? Because energy is being conserved, which means the energy gained, Q gained, plus Q lost have to equal zero, right? Where the Q gained will be maybe at plus 1,000 joules, Q lost will be minus 1,000 joules, right? And then 1,000 plus negative 1,000 gives you zero. Or if I rearrange that and take my Q lost to the zero side, it becomes negative Q lost. So Q gained equals negative Q lost, or Q lost equals negative Q gained. It doesn't matter which way you do it. Okay, and that's it. So we're just going to be using mc delta T, except we're going to do it twice now. So let me look at the sample questions here. There are 3 sample questions for section 2.3b. Right, the first one is a 60-gram piece of metal is being heated to 100 degrees C. All right, so it's being warmed up, and then I'm going to place it in 200 milliliters of water, which is at 10 degrees C. Now, typically how we do this, right, if I want to heat something to 100 degrees C, I'm just going to drop it in boiling water, because I know boiling water boils at 100. It won't be boiling at 95, and it won't be boiling at 105. It'll be boiling at exactly 100 degrees C. So if I drop my metal into boiling water, right, it will now get to 100 degrees C because of thermal energy transfer. It's going to absorb energy from the hot water around it. But again, we're not looking at that part. What I'm looking at is if I take it out of that boiling water and drop it into a beaker now that has 200 milliliters of 10-degree water, what's going to happen? Well, the metal is going to cool down and the water is going to warm up. Right? Now, what I need to do here is I need to set this up as in a format where I'm going to be able to deal with all the numbers in this question. Again, as with some of the other things that we do, a lot of the answer is based upon the way we set this up. So if I do sample question 1 here, okay, I always set these questions up the same. I say something hot is being added to something cold, and then ultimately I'm going to end up with a final situation. Okay, and you think, okay, I guess, yeah, that makes sense. Doesn't look like much of a chemical equation, even though I've set it up as a chemical equation, but that's just because I've been doing chemistry for too many years. So if I look at this, I say, what's hot? Well, the hot is that metal. Now the question actually says, let me go back to the question just for a second here. Question says, determine the identity of the metal. Okay, that's what the question's asking you to figure out. What is the identity of the metal? How am I going to do that? Well, I'm going to have to figure out C for the metal mathematically, and then once I know C, I can use that to determine what metal it is. So I'm going to go back to my whiteboard here, and I'm going to say, okay, hot is the metal, and the cold, is the water, which I'm putting the metal into. I know the T1 for the metal was 100 degrees Celsius. And I know the T1 for the water is 10 degrees Celsius. Should be 10.0 degrees Celsius. And I know that the final temperature is 15.6 degrees Celsius. Now, that final temperature is the final temperature that the water is going to get to. And it's the final temperature that the metal is going to get to. So the metal is going to cool down to 15.6 degrees C, while the water is increasing temperature from 10 to 15.6 degrees C. I know the C value for water. The C value for water that our textbook is using is 4.18 times 10 to the 3. times 10 to the power of 3 joules per kilogram degree C. The C value over here is unknown. What else do I know? I know the mass of water, and I know the mass of my metal that I'm going to warm up, that I'm going to cool down. The mass of the metal is 60.0 grams. 60.0 grams. Again, let's do my conversion. I know that 1 kilogram is 1,000 grams. So this is 0.0600 kilograms of metal. And if I do the same thing for the water, we're told that we have 200 milliliters of water. Oh, but every milliliter is a milligram. So the mass of water is 200, come on pen, 0.0 grams, or 0.2000 kilograms. Okay, so I now know my mass for my cold water. So if I look at what I have in terms of the math here, what I know is that the Q on this side, which is going to be lost, is going to be equal to the Q that's going to be gained by the water. But again, remember, I need a negative sign in here, right, to make this work. So if I start putting my numbers in now, I know Q is equal to M C delta T, M C delta T for the metal will be equal to the negative M C delta T for the water. So let's put our numbers in now. I know the mass for the metal, 0.0600. The C value for the metal is unknown, but I know delta T is T2 minus T1. It's 15.6 minus 100 degrees. On the right side, my negative sign, remember, I've got the mass of the water, which is 0.2000 kilograms. The C value for water, and my delta T for the water, T2, 15.6, minus my starting temperature, 10 degrees C. Now I'm going to do the math on the left side, so I'm going to take my 15.6, I'm going to subtract 100 from it, So I'm getting negative 84.4, and I'm going to multiply that times 0.06, and I'm getting negative 5.06 C on the left here. On the right, I'm going to again take my 15.6. I'm going to subtract from that the 10 degrees, multiply it times my 4.18 times 10 to the third, and multiply that 0.2 negative, and I'm getting 4682. So now to solve for C, I'm just going to divide the right side by my negative 5.6, and I'm getting 925 joules per kilogram degree C. And then if I go to my chart and say what has a specific heat capacity of 925, if I can find the chart, it's telling me aluminum is 920. Okay, so it's probably aluminum. So therefore, I can't say for sure it's aluminum because there's a whole lot of metals that aren't on my list. And there could probably be other metals that are 920 or 925 joules per kilogram degree C, but I don't know what they are. But I do know that aluminum is one possibility because it matches. Right? So I'm not going to say for sure that it's aluminum because for all I know, chromium could be 925. It's just not on this list. Remember, there's only, I think how many are on that list. There's probably only 8 or 10 metals on that entire list. So that being the case, it's not even. There's aluminum, iron, copper, silver, lead, right? 5 metals out of periodic table must have 75 metals, right? So, like I said, I'm going to assume that it's probably aluminum, but I'm not going to say for sure. I could even be safer and say, not even probably, I could say it could be aluminum. And again, that might even be a better choice here than saying probably. If I look at sample number 2, it says a sample of iron is heated to 80 degrees and then it's placed in water at 20 degrees and the final temperature is 22, and it says how much iron did I use? Okay, so let's go down to my whiteboard and let's do the same thing that I just did a moment ago. This is sample number 2, and I've got a hot plus cold. Okay, I know my hot in this case, go back to my question here, is my hot in this case is the iron, which is 80 degrees C. .0 degrees C, and my water is the cold thing, and it's at 20 degrees C. Okay, 20 degrees C. Oh, sorry, 22 degrees C. Some dexterity issues here, more than usual. 22.0 degrees C. And my final temperature is going to be, oh, the final temperature is 22. I'm sorry, I'm not reading my question very well here. 22.0 degrees C. My starting temperature over here was 20 degrees C. I was right in the first place. Okay, so I now know what my T1s and T2s are. I can put my T2 here because I know that it's going to finally end up at 22 degrees C and that the water also will reach 22 degrees C. It'd be impossible for you to read my writing. Okay, so try my other stylus here. Okay, so I now know T1 and T2. I know the mass of cold water. Mass of cold water was 100 milliliters, which means 100 grams. Okay, so just keep that in mind for water. 100 milliliters is 100 grams. 1 milliliter is 1 gram. I know that this is water, so I know what the C value is here. 4.18 times 10 to the power of 3. And on the left side here, I have iron, and the C value for iron is 4.5 times 10 to the power of 2 joules per kilogram degree C. I'm not going to attempt to write that. So on the right side here, I see MC and delta T. On the left side, I see C and delta T. I'm missing the mass, which is what the question is asking. How much iron did I put in the water? Okay, so now I'm going to say that my Q Q lost by the hot item is going to be equal to the negative of the Q gain. The Q gain to be positive answer, but I need to make it negative to show how much Q lost there was. So let's put our numbers in here. I know that I have MC delta T for the lost. It's going to be equal to negative MC delta T for the cold. Again, notice that there's a lot of numbers going on here, right? Just try and keep your columns. So the mass here is unknown. My C value here is 4.5 times 10 to the 2, which is 450. T2 minus T1 is 22 minus 80. On the right side, I have a negative sign. I know the mass. I'm going to have to convert that to kilograms. So I have 0.100 kilograms times the C value for water, 4.18 times 10 to the power of 3 times my delta T here, which is T2, 22 degrees, minus starting temperature, 20 degrees. Should be a minus sign in there. And now I'm going to, again, do my math on the left. So I'm going to take 22 minus 80 times 450. I'm getting negative 26,100 M on the left. On the right, again, I'm going to take my 22 minus 20, which is 2 degrees C, times 4.18 times 10 to the third times 0.1 kilograms. I'm getting negative 836. So I'm getting a mass here, which is, again, notice the negative signs cancel, of 0.0320 kilograms. Right, or 32.0 grams. Again, it doesn't ask you to calculate an answer in grams, right? But if it did, right, you just have to do your conversion of grams, kilograms to grams. Okay, so there's question sample 2. So the first one was asking you to calculate a C value. The second one here is asking you to calculate a mass. And then the last question up there, so let's just go back to sample 3, and I will do sample 3 for you. Sample 3 says, during an investigation, 200 grams of silver is heated to 90. The hot silver is then placed in 300 grams of ethanol that has an initial temperature of 5 degrees C. Determine the final temperatures of silver and alcohol. Okay, so this one gets, you're going to see in a moment, this one gets a little more complicated. Now, okay, so for sample 3, okay, hot plus cold. Okay, so I've started with a hot thing and a cold thing, and then I end up with a final set of final temperature. Okay, so To start off with, I've got 200 grams of silver. So the mass, 200.0 grams, or 0.2000 excuse me, kilograms. I know the C value for silver is 2.4 times 10 to the power of 2. Joules per kilogram degree C. And I know the starting temperature. Starting temperature was 90.0 degrees C. Okay. I don't know T2. Let's go over to the cold stuff. The cold stuff is ethyl alcohol, and it says the ethyl alcohol has a mass of 300 grams. Which I've converted to kilograms here. I know the C value for ethyl alcohol from the chart is 2.46 times 10 to the third. Times 10 to the power of 3 joules per kilogram degree C. And I know the starting temperature for the alcohol was 5.0 degrees C. Okay, so now I'm kind of stuck because I don't know any more information from the question. So I'm going to say, what can I set this up in a way Q on hot is equal to the negative Q cold. So I'm going to take my MC delta T here equals negative MC delta T for the cold. Okay, the mass is 0.2. Times the C, which is 240, times T2 minus my T1, which was 90 degrees C. Okay, so I've got a T2, which is on that side, which is my unknown. Okay, unknown. Okay, so there's my required to find is final T2. If I remember correctly, it is. Okay, so I need to make that equal to what's on the right side, which is the negative of the mass, 0.3 times the C value, 2460, 2.46 times 10 to the 3, times T2 minus T1, which was 5 degrees C. All right, so let's, again, now your algebra skills are going to kick in, and we're all going to have slightly different ways of doing this. So I've got 0.2 times 240 on the left, which is 48, times T2 minus 90. On the right, I have 0.3 times 2460 negative. I'm getting negative 738. Negative 738 times, this T2 minus 5. So I've got to multiply my 48 into the brackets, so I get 48 T2s minus 48 times 90, and I'm getting 4320. On the right side, I'm taking my negative 738, if that's what it is. 0.3 times 2460, 738 times T2, negative 738 T2s. And then negative 738 times negative 5 is plus 3690. Right, now I'm going to take my T2 terms, this one here and this one, to the left side. So I'm going to end up with 48 T2s plus 738 T2s. On the right, I'm going to end up with my 40, whatever that number is, 4320. Boy, this writing is terrible today. I'm going to take my negative 4320 across as plus 4320 plus my 3690. Okay, I'm going to add up my T2 terms, the 738 and the 48, and I'm going to add my 4320 plus 3690, and I'm going to get 8010 on the right. On the left, I'm going to have my 48 plus 738 T2s, which is 786 T2s. So my T2 now will be 8010 divided by 786. I'm getting 10.2 degrees Celsius. Okay, 10 degrees Celsius. Let me go back to my original question, and it says that the metal was at 90, the ethanol was at 5, so I've got to have a temperature somewhere in between there, and I did. I've ended up with a final temperature of 10.2 degrees Celsius. Again, if I'm getting an answer which is 3.1, I know it's impossible because I can't add 90-degree metal to 5-degree alcohol and end up with the temperature dropping. If I end up with an answer of 468, again, I know it's impossible. So again, just look at your question and see whether the answer that you're getting makes sense, if it's a logical answer based upon the question being asked. All right, so hot plus cold, Q equals negative Q, so MC delta T equals negative MC delta T. Okay, so there are two questions here in the practice. The answers, again, are given for you. One's asking you for a temperature. One's asking you to calculate a C value. There's a bunch of review questions here. I'm going to ask you to work on these questions here. Again, questions 9 and 10 are probably not that important at this point in time. I would just work on questions 1 to 8. And then if I go back to my note, so there's questions 1 to 8. There's the questions 1 and there was actually, I think, just 1 and 2 actually in the practice. And then there are some questions in our textbook. I'm going to suggest you look at the examples that are in the textbook that they've done for you, and then they've given you 4 more questions to practice at the end of the chapter. All right, so that should get us through all of our notes for this week. So I'm not planning on doing anything more now until Wednesday of next week, when we'll come back to our Q values again. So for now, I encourage you to go ahead and do all this work, and then maybe on Tuesday night or Wednesday, come back and maybe just revisit these again one more time before we move into our new note on Wednesday of next week. If you double check the calendar, you'll see a lot of updated dates that are in there. So I encourage you to go to the calendar and see what's going on. And then from there, hopefully you're ready for the lab. I can't encourage you enough to do the lab before next Tuesday. Right? There are 1 or 2 questions. I'm not totally done the test yet. That will be exactly the same as the lab question. If you've done the lab, they'll be easy. If you haven't done the lab, they're going to be maybe even impossible. So definitely take the time to do the lab. If you get stuck between now and Tuesday, again, ask a question and then let me know and remind that you've posted the question, or you can just post the question directly to me and remind, and I will try and answer it for everybody. Okay, so you take care. I'm not planning a live session again. Hang on a minute here. Oh, sorry, our ISU is on Wednesday, so I am planning a drop-in session if you have any questions about the ISU on Tuesday morning. All right, and then it'll be Wednesday night then when I post the next note for Energy 2.4. Okay, and then we're rattling through this. So by then we're at 1 week left in May. By this time next week, we should know whether we're going back in June or whether we're going to be off until the fall. And we'll go from there. So have a nice weekend. Try and get as much work done on your ISU. Hopefully it's finished. And then just read it over. Go over the video that I've posted for sound. I think it's a very thorough look at most of the topics that are on the test. The test is going to be largely multiple choice theory questions with about 10 quick calculations. And the calculations, are pretty straightforward. V equals 332 plus 0.6 t to find the speed of sound. V equals f lambda, the universal wave equation. F equals 1 over period.